So you might have that it is minus 10 meters per second squared, or you could have that it's minus 9.8 meters per second squared. Either one's okay with me. Okay, for part B, it says, upon reaching a downward velocity of 100 miles per hour, so velocity, I don't know, this is probably its final velocity, right? Of 100 miles per hour. 300 newtons of drag resist the diver's motion. Draw a force diagram for the skydiver. How large is the skydiver's acceleration? So I'm going to write down what they're telling us first, is that our final velocity is 100 miles per hour. Our drag is 300 newtons, and it's asking for his acceleration. Okay. So our force diagram here is going to have a downward force due to gravity, which we can solve, right? Because we know that that's going to be mass times acceleration due to gravity. So that should be 70 kilograms times minus 10 meters per second squared. Upward, he's going to have drag. And we're told that that drag is 300 newtons. So I'm going to calculate my downward force due to gravity here. Well, I don't even need to. It's going to be minus 700 newtons. And that's bigger than my drag, right? So this is telling me that our skydiver is definitely accelerating downward, for sure. If we remember, the equation for our net force is going to be, our net force is equal to the total mass times the overall acceleration, and that's going to be equal to the sum of all of our forces. So our Fg plus our drag. So what we need to solve for now is this acceleration. We know that the mass of our skydiver is 70 kilograms. We're solving for acceleration. That's going to be equal to our minus 700 newtons plus 300 newtons. Doing okay so far? So I've got 70 kilograms times acceleration equals minus 400 newtons. So acceleration equals minus 400 newtons over 70 kilograms. So I got minus 5.7 meters per second squared. It's always important to have those units. And since it's acceleration, I know that they're going to be meters per second squared. If we wanted to solve, sorry, that's hard to see. If we wanted to solve for our units, we could do that. Remember, newtons is going to be equal to kilograms times meters per second squared. So that's how we could kind of figure out what the units ought to be for this if we wanted to solve for those units. You guys have any questions about number 5? How did we do? Okay? Yeah? All right, let's try another one. Draw a force diagram for a 900 kilogram car that exerts 5,000 newtons of traction force on a level road while being opposed by 1,000 newtons of friction and drag forces combined. So first we need to draw a force diagram, which is what it tells us to do. You guys should have done this a while ago, right? So we're going to have gravity downward, normal force upward. Let's see, which direction should be forward, to the right or to the left? Any votes? I'm going to make them go to the right. So I'm going to call that my traction force. And then backwards is going to be our drag and air resistance and all that stuff. We know that our mass of our car is 900 kilograms, so our force due to gravity must be minus 9,000 newtons. Sorry about that. Is being opposed by 1,000 newtons of friction and drag forces. So since this is, I've decided that way's forward, I'm going to make that positive and make drag negative. So I'm going to say that this is going to be minus 1,000 newtons. Next, it says write a net force equation for the car. So my net force equation is going to be equal to mass times acceleration from Newton's second law, and also the sum of the forces. There's actually going to be two equations, right? We could write one for vertical and one for horizontal forces. But since it's going to ask us to do acceleration of the car, I'm going to do this for the horizontal forces. So my horizontal forces are drag and traction. There's my equation. It doesn't ask me to solve anything, does it? So I'm not gonna. Next part says calculate the acceleration of the car. So to do that, I don't know what my net force is. I do know my mass of my car. I'm calculating acceleration, and I'm given drag. Oh, and it gives me traction force, and I didn't write it down. Okay, so I have all the information that I need to be able to solve for this. So one way that I could approach this, I could do what I did in the other equation and fill all these in. The other thing that I could do is rearrange my variables and then solve. So I could rewrite this so that I have acceleration is equal to my traction force plus drag divided by the mass. So my traction is going to be 5,000 newtons. Drag is going to be minus 1,000 newtons. And that's going to be divided by the mass of the car, which is 900 kilograms. And again, we're looking for an acceleration, so I know my units will be meters per second squared. I'm going to have 4,000 divided by 900. And I'm going to end up with 4.44 meters per second squared. Hi, Lucas. Did you drive okay today? No. No? Nah. Were you part of the incident in the parking lot?
No, I don't think so.
Okay, I don't even know what that was. But you just reminded me I need to do attendance. All right, number 7, guys, this is our Atwood machine problem. So we played with Atwood's machine last week, and that was so that we could all get the opportunity to kind of see what Atwood's machine was like. I think I made a bit of an error when we were talking about Atwood's machines, though, and it's one of those details. I don't think that it means that your results were not valid, because it's just the small mistake with the Atwood's machine is that when we're thinking about the mass of what is moving, we have to include all of the mass, and so we intentionally leave out parts of that. So when we did our experiment, we weren't really worrying about the mass of the car, for instance. But when we were doing the experiment where we were adding mass to the hanging mass, what we should have done is had the parts that we hadn't added yet on the car, so that they still had to be part of the system that was moving. But we're gonna do these problems, and hopefully that sort of issue kind of makes sense to you after we've looked at these, because these are a little bit more straightforward than doing the experiment. So we have 3 modified Atwood's machines below, and they have blocks that are attached to them. Each of these blocks is an equal amount of mass. They're on a frictionless surface, and everything's hanging from a string. When the blocks are released, they accelerate just like they did in our lab. Only here they're using a frictionless surface instead of wheels. So it says, first, which system has the greatest net force? Explain how you know. Which one has the least inertia? Explain how you know. And determine the acceleration for each system. All right, so how are we going to do this? What do you guys think of this problem? Was it tricky? It's kind of hard to think about it, right? So let's see. Every one of these guys is going to have, let's see, we're going to have some forces. System A here has 1 mass up here, right? And then there's a string, and then another mass. The second one has a bigger mass. I'm going to label this one 2m, and then m. And then over here, we've got m attached to a 2m block. Do you guys see that? See how I simplified that? So we're just looking at how they're attached. Then what we can do is we can think about what are the forces that are impacting these systems. So here we're going to have a force that's related to 2m. And so this amount of force here is going to be equal to mass times acceleration. In this instance, the amount of force that that purple arrow represents is just going to be the one hanging mass times acceleration due to gravity. So I'm just going to write MA right there. This one, same thing. We just have one hanging mass. So this force is going to be equal to mass times acceleration. This last one is going to have a force going downward, but look at this. There's twice as much mass. So do you guys remember in your experiment when you hung more mass on the string, did your car go faster or slower or the same? You guys remember? If you put more mass on the hanger, did the car go faster, slower, at the same speed? It went faster, yeah. So now when we calculate our force, that's going to be equal to 2 times mass times acceleration. So if we are just looking at the force in that direction, if we have a frictionless surface and there's nothing going back the other way, which one has the biggest net force? Which one of those three, A, B, or C? Anybody think A? B? C? Yeah, it's going to be C because it's got twice as much mass hanging there. So this first one will be C. All right, because because twice the hanging mass. All right, this one's trickier because we haven't really talked much about inertia. Which one has the least inertia? A good way to think about inertia is the one that has resistance to being pulled backwards, right? So which one do you think is going to be the most resistant to moving? Anybody think A? B? C? I saw a couple of nods for A and a couple of nods for B and a definite no for C. Right, C's got the most force. So that's going to be the one that's easiest to move, right? We observed that when we set up Atwood's machine and we put more mass on it, that it was easier to move the cart. These two are a little bit trickier, as if we're thinking about inertia, we're thinking about resistance to motion and which one wants to move the least. Which do you think is harder to move? Something that has more mass or less mass? More mass is harder to move, right? And so the one that's going to have the least inertia is probably going to be A because it's the lightest, right? A. Then it wants us to determine the acceleration for each system. How do we do that? Can we figure out what the mass of each system is? And we can figure out the force? This is tricky, right? I'm going to set up a little table. Dang. We'll set up a table tomorrow.